Welcome everybody to LLM Engineering Cohort 3, hashtag LLME3, Session 9. We are going to finish up alignment, such a big topic, by showing some more details of DPO and actually doing a build with direct preference optimization before we move on to model merging and really talking about the SLMs, the small language models that we started learning about in the beginning of the course and that we'll continue to see more and more of in 2025. But first, we're on a mission over here at AI Makerspace this year into next year and far beyond to create the world's leading community for people who want to build, ship, and share production LLM applications. Shout out to the legends Sahar, Nalay, and love to see this, Ryan getting in on the action this week. Okay. The build, ship, share muscles are starting to get stronger. Absolutely love to see it. Now, if you're looking to get after it with some accountability, we've got one more meeting this year, then we're going to take a week off. So we'll meet next Monday, then we'll take a week off, and then we're back at it for the new year. And there will be a lot of building, shipping, and sharing happening just as soon as we launch our next cohort on January the 14th. So it's going to have a lot of energy. There's going to be a lot of folks getting into the Discord. There's going to be a lot of things happening as the year kicks off. We're really, really excited. But as we sort of let the sun set as the winter solstice approaches this weekend, we also would invite everybody to join us for our last event of the year live. This is going to be on-prem agents with LangGraph. Should be pretty fun. Cover exactly how the rewards model and the rewards mechanism works within the context of a PPO scheme and KL divergence. This is a really great piece of feedback. And I just want to kind of point out that like PPO algorithms are sort of a class of optimization algorithms. And it really came out of the RL research that was going on at OpenAI back in 2017. And, you know, you can kind of just see that really this very much did come out of RL, new family of policy gradient methods for RL, which alternate between sampling data through interaction with the environment and optimizing a surrogate objective function. So this idea of like objective functions, surrogate models, gradient descent, stochastic, all this kind of stuff is all really hardcore optimization and statistics background. And the KL divergence idea actually came from this paper in 1951. So you guys kind of started to inspire me today to really go back and revisit the depth of loss functions, perhaps in 2025. So if you'd love to see some really deep theoretical mathy events in 2025, digging into loss on a foundational level, smash the chat and please let me know or DM me in Discord. As we align our aim, we are now kind of, the sun is setting a little bit on the year and a little bit on the course. Here we are. We're not going to quite get to distillation today. We're going to cover distillation and frontiers next time. We're also going to have a fun sesh. We're going to have the AIM games. It's going to be a banger. It's going to be a blast. And we really, really encourage everybody to join us. So we're really kind of out on the frontier once we cover alignment today. And that is kind of going to give you guys all a real good foundation about LLMs all the way up to SLMs. So we're going to talk DPO today. We're going to talk how to do it, how we can use it for similar reasons that we used RLHF before. We're going to talk model merging and the algos and how this is being used in practice today. All right, so we're going to talk alignment. We're going to talk merging, and we're going to build both. And we should have time for QA at the end. All right, DPO, the reason why we need to talk about it is because it's the standard today. If you read the Llama 3 Herd of Models paper, you'll be able to see the overall architecture. This is something that we're pretty familiar with now. Token embeddings, etc. And you'll also see that the overall post-training approach for Llama 3 included this DPO training. So let's take a look at what they said. Now, we're taking the training wheels off today, guys. This is straight from the paper, Managing Complexity. We make design choices that seek to maximize our ability to scale the model development process. Hype. We opt for a standard, dense transformer model architecture and adopt a relatively simple post-training procedure based on supervised fine-tuning, rejection, sampling, and direct preference optimization. We chose DPO as opposed to a more complex RL algorithm that tends to be less stable and harder to scale. Okay, you guys tracking with this language now? Language model post-training, let's go deeper. The pre-trained language model has a rich understanding of language, but it does not yet follow instructions or behave in the way we would expect an assistant to. We align the model with human feedback in several rounds, each of which involves supervised fine-tuning on instruction tuning data and DPO. Remember, our optimization objective is exactly to do this well. And it turns out Llama 3.1 is actually super well aligned already. Like, it's like really good, you know, and you notice we're kind of like barely getting improvements last time. So we decided to opt for a slightly worse model off the shelf called Mistral 7B. Now, Mistral, if you read the technical report here, this is actually from October 2023. They're obsessed with comparing themselves to Llama 2. And they did do slightly better. We fine-tuned on instruction data sets, a classic move, Mistral, instruction fine-tuning. And then insofar as they did alignment, it kind of looked like this. We introduce a system prompt. The system prompt reads, always assist with care, respect, and truth. Respond with the utmost utility, yet securely avoid harmful, unethical, prejudiced, or negative content. Ensure replies promote fairness and positivity. Sound a little constitutional, isn't it? So they used a bunch of prompts and they said, look, ours is a little bit better. Hype. And they really didn't do much more alignment work. Although they did add this little sort of self-reflection capability, the model itself was actually able to classify a prompt as having been associated with one of the following categories: illegal activities, unqualified advice, etc. So when we do DPO today, when we pick a model like Mistral that wasn't like really well aligned, we're going to be able to see huge gains. And that's what we want to see when we do alignment. Just to kind of put this into perspective here, into the sequence of the timeline of where we are today, it's basically forever ago that the Mistral 7B technical report came out. So it's not really surprising that Llama 3 Earth models is crushing it. So let's talk about DPO. As we briefly mentioned, RL can be a little bit more unstable. It's a completely different ML paradigm. It requires 3 different models. And, you know, that's probably not something that is necessarily going to be useful in all cases, as they mentioned in the Llama 3 paper. More complex, less stable, harder to scale. So DPO says that your language model is the reward model. That's what it says. So the LLM is already able to act as the reward model. There's a lot of fancy math that goes into this, okay? But we remove this complexity of this paradigm. That's the big idea. We remove it, which is hype, by directly optimizing. And it directly optimizes, I'm going to give you some intuition behind this, using a simple classification objective. Okay, a simple objective and an implicit reward function. So I can't actually write down the reward function, although I can derive it. And it is derived in the paper. And this is the kind of thing that I would put together in a more detailed event on this. It's implicit, so it can be derived, but it's not explicit in the way we calculate loss. This equation, this analytical mapping, is the whole point. That when we have this equation, we can then optimize and do our alignment in a much more direct, straightforward way. And so it looks like this, as we talked about before. We put the prompts in, X is the input, we get some Y out of the reference, some Y out of the policy model. We're going to check for a little KL divergence, and then we're going to get a score associated with model 1, get a score associated with model 2, calculate a loss function based on that. Then, based on that calculation of loss, we're going to update the lower weights exactly like we do in all training and fine-tuning. Okay, so let's talk about this loss function for a second. It looks like this, and it looks a little bit scary, and it shouldn't, okay? Because check this out. X is the prompt that goes in. Look at X. So I have the loss of DPO, and I have pi sub theta, this is the policy model, and I have pi sub reference, this is the reference model. So these are the two models, okay? Equals this expected value. Basically, I'm pulling X, Y winning, Y losing. That one's better, that one's worse in terms of toxicity out of this distribution. And then I'm calculating this thing. Okay, I'm calculating this thing, and this thing that I'm calculating is actually not so different than much simpler things that you've calculated and probably become familiar with before. Beta is just this parameter that allows us to sort of say, how much are we allowing the policy model and the reference model to actually deviate from each other? It's associated with the KL divergence. And the formula overall here is really, I'm going to give you the intuition behind this. Okay, I'm going to give you the intuition. It looks a lot like stuff we've seen before and feels a lot like stuff we've seen before. Recall from session 6, we talked about pre-training. We talked about cross-entropy loss when we looked across targets and logits. And when we then calculated the actual cross-entropy loss, the targets versus the logits they're actually calculated after the softmax. So the softmax, as we saw in code, it's actually easier to calculate softmax and then do this. The softmax is calculated based on the logits with this equation right here. Now, it's interesting if we go back to DPO, this sigma is the sigmoid equation. The sigmoid equation works on a single value of X in this case, whereas the softmax function, the softmax works on a vector. It outputs a probability between 0 and 1, potentially for a single value or for an entire vector. This one doesn't output a probability, it doesn't output a probability distribution, it outputs a single number. That single number, if you'll remember from sort of classic ML, if it's like greater than 0.5, you say, okay, positive. If it's less than 0.5, you say, okay, negative. And the sigmoid function, as in a simple classification problem, ensures that the loss is bounded and that the optimization process is relatively stable. So really, it's kind of like we're seeing, okay, I'm going to look at this term that has the pi sub theta. This is the policy model. I'm going to look at the wins given the inputs. I'm going to look at the reference model, the wins given the inputs. Then I'm going to have this term for the losses given the inputs on the policy and on the reference model. And so you can really kind of start to see and intuit the connection here. And when you read the paper and you read that we can optimize this thing exactly with a simple binary cross entropy objective, it sounds exactly like what you would expect. There's a ton of really sophisticated math and statistics and theorems and lemmas and all of the good stuff if you went to sort of deep into statistics in grad school or elsewhere. I encourage you guys to check it out, and maybe we'll check it out together sometime. But in the end, we don't really need this reward model. We instead can do this much cleaner optimization scheme. So that's what we're going to do today. And we're going to do it on Mistral Instruct v0.3. So again, this was instruct tuned. It just wasn't aligned like super well, like some of these off-the-shelf llama models. And the steps to DPO are the same as the steps to what we needed before. We're going to get the data in the right format. There's a little tweak for the Mistral model that Wiz will talk about, and then we're going to perform DPO. That's it. Wiz, show us how it's done.
Last time RLHF was hard. This time DPO is easy. We have the, the basic ideas Greg's already highlighted for us. We just need to make this model more betterer at the things we want it to be more betterer at. And the way that we do this with RLHF, it involves translating this problem into a whole new domain, right? Which is tedious, as well as it's slightly inefficient. And so DPO helps us keep it in the same domain. Like Greg mentioned, the brunt of the alignment done to the Llama 3 herd of models is using DPO, though for fine-tuning, instruction tuning, they're still going to use RLHF. RLHF still has a place in the ecosystem. It's just why translate if we don't have to, right? If it's not for something. So in order to start with this, we need the same library that we used to do RLHF. This is TRL. This has basically become like the alignment library for Hugging Face. So Transformers does all of our transformery things, and TRL does all of our alignment-y things. Make sure we have a GPU, make sure we have some configs, everything's kind of normal, and then we're going to get a baseline for our model, classic. We're going to also use bits and bytes, exactly the same as we used it before. We're going to use Mistral 7B instruct v0.3. This is the most performant version of the Mistral 7B model. And we'll set up our tokenizer. And then we'll look at, what our model looks like. And there's a question about this, right? Which is that this seems to be a different model. I mean, it's called Mistral. But this stuff was looking pretty familiar, right? Pretty exactly the same as what we've been using before, right? So the question is just going to ask you, is this similar in architecture to Llama 3.1, AP instruct, and then create a map of what these are called in each of them. And I think you'll find very quickly that they differ in name only for a lot of the architecture. We're going to go ahead and use the same data set that we used last time, which is the HHRLHF data set from Anthropic, where we're going to provide our, everything in this specific prompt format. This is just formatting that. And then we can go ahead and look at our final training set, which is just going to be 500 rows of our train set. And then we have 10 and 10 for test and val. And that's it. Then we can create some responses to the test set with our reference model. Great question by Nalay in chat, right? Which is talking about, what is the reference? What is the policy? So the reference model is like, that's the model we don't want to get too far from, right? So but it's not yet good at the thing we want it to be good at, right? It's not safe in this case. It's still a little bit toxic. And so the idea is our reference is what we're just tying our policy down to. Our policy is the thing that we're actually going to train. So it's the thing that is going to be what they're going to be is the final artifact of this process, right? It's like the model we're going to walk away with. But the idea of the reference is just to make sure we don't drift too far. Because what you'll find if you use DPO and if you put the learning rate up a little bit and you train for a few more iterations, very quickly your model is going to be very good at producing many commas in a row or many dashes in a row, which is not desired behavior, right? So the reference helps us get tied to that base model. And that's why we have a reference. We get some responses. You can read them if you'd like, but the idea is that, again, they're not super toxic. The max toxicity is not super high. This should be expected, right? Companies are not in the habit of releasing very toxic models these days, and indeed we see that being true. So we're going to still use DPO, right, in order to make it even less toxic. We're going to use LoRa again, classic LoRa. We're always using LoRa. Fine-tuning and LoRa mean the same thing these days, right? Like doing full SFT is something that you're only doing at very specific shops. Most times that we're fine-tuning, we're talking about LoRa because the cost savings is absolutely ridiculous. Then we have to set up our training arguments. This is kind of normal stuff, except we're not using the Karpathy constant for our learning rate. We're using this very small learning rate. We don't actually want this model to learn a ton. Again, if you're overzealous in training with DPO, you're going to absolutely tank the model with the hyperparameters that we have set up. Nalay is asking, is quantization a necessary step? No. It just happens to be one we do a lot because we're in a compute limited environment. But you don't have to do quantization to use LoRa. And you don't have to use LoRa if you've done quantization. We're going to use this loss type of sigmoid, which is a good loss. I'm going to ask you guys a question, which is to describe each of the losses available to us. Here they are, along with the papers that they come from. And basically, this loss, right, is an extension or a modification of that big kind of gross looking equation that Greg showed us. Again, because we're leaving this in the domain of LLM cross entropy loss world, right, we don't have to do this weird conversion to PPO land or RL land. We can get kind of fun with our loss, right, and just adapt it based on what we're most excited about. Our default, of course, is the sigmoid that we were shown, but that's it. Beta is, how far can we stretch from that original reference model, right? So we're going to keep our beta relatively low here. It could be even lower, but for now, we're just going to leave it like that. And then, of course, we have the training process, which is going to include more words than we're used to, right? But this is there's some text in here that's going to express what those words are about. And the idea is that we're not just looking at this train and val loss. We actually have some insight into what we're choosing, how often we're choosing it, are we right when we're choosing something, when we're doing our evaluations. And this is just giving us much better insight into how our training process is going. Also, I'm going to ask you to determine if the final checkpoint, that's this one, right, the 250th step, is the best checkpoint in the run. This is going to build some intuition that is important, which is that we often train models and think of things as having this, best checkpoint training paradigm, where we don't actually always just have this this naive kind of understanding, like, oh, well, the last one's probably the best. Oftentimes, the last one is definitely one of them, but very rarely is it the best one when we're training these models. This is due to the fact that loss is a little noisy. As we go through, depending on what metrics we care about, we'll be able to pretty quickly determine if this is or not the best checkpoint at the end. And if it's not, why? Okay. And then we have DPO, we save it, classic, we load it, classic, we generate some text with it. Of course, that's also classic. And we see that we have a reduction in our toxicity. So we went from 0.03 to 0.015. I mean, we cut toxicity in half, right? Not bad. Not bad for a day's work of 250 steps of training. with a relatively small data set. And then, of course, our max toxicity is ever so slightly lower, less impressive, but still good. And this is just showcasing the power of these techniques, right? We have 500 samples in our data set. We trained for 250 steps in a Colab notebook, and we made Mistral less toxic, right? This is why DPO is useful. This is why post-training, pre-DPO used to be like, do I really care about this alignment thing because I have to do this RLHF stuff and it's big, it's complicated, and it's not stable when I'm training it and all this blah, blah, blah. Now with DPO, the answer is just for sure. Yes, you should definitely just do post-training, right? DPO makes it easy. It's fast. And as we can see, it does a good enough job.
Let's go. Thanks, Wiz. Let's go ahead and spend some time together. We got to load an instructing model. We got to baseline it, and then we're going to train using the DPO trainer. Should be pretty straightforward. You guys can chat about alignment. We've got some nice groups ready for you. Okay, now that we're back from the break, let's go ahead and just, take a quick look at a couple final takeaways here. Number one, this is a great quote to sort of just think about. Why would some experts say this? And, we talked about RL today. We talked about how, and even as we can sort of kind of think about how the future is going to go, maybe there's a little reinforcement learning like pull happening with some of these reasoning models and some of the interesting things happening at test time compute. Reinforcement learning is a massive field. It's so much bigger than RLHF, but RLHF is still something that you're going to need to know is going to be around for quite some time. And we're still, as we saw last time, trying to do things like mixture of judges, take RLHF to the next level. So knowing both of these techniques we thought was quite worthwhile, and something that hopefully you found worthwhile as well. Yeah, RLHF really doesn't fit in well with the rest. We did see a huge improvement with DPO though, and that's pretty great. So again, I want to just triple down on this. Don't forget this point. Anybody that's watching this, if you are the only person in your company as you go and you build, ship, and share some production LLM applications that remembers to do some alignment at the end, that will really potentially add some additional value. And again, you don't have to align to reduce toxicity. You can align to literally get better at anything. At anything. It's just optimization in the end. But there's other ways to optimize, and that's where we go to next. We go to one of the techniques that has been quite slow to get adopted by the industry because it was kind of looked down upon for quite some time. And now it's getting some steam. It's getting some action. Model merging is a simple idea. We have all the weights over here. We can download them. We have all the weights over here. We can download them. Can we just merge them? Yes, we can. And it actually kind of works, which is just crazy that it kind of works. It works to improve performance. Good at task A, good at task B, good at both task A and task B. The intuition is there, and actually it is backed up by the programming. And we don't have to spend really like, we're like spending pennies here, okay? This isn't like a huge compute lift. This is just literally taking floating point numbers, taking other floating point numbers, and the simplest possible thing to do, as we'll see, is just average them, literally. And as we saw, when we're releasing state-of-the-art models today, we're doing things like this. We're taking a massive model. Great question in the chat on LoRa adapters. There's a really nice intuition that we're going to connect into this in just a moment. When we looked at RC, the Supernova 70 billion model that just came out, we saw that they distilled Llama 3's 405B instruct. Then they fine-tuned a few other LLMs. They aligned some stuff. They merged them all. Let's take a closer look at this. On the DPO and final model merge, they had their third version of Llama 3.1 70B instruct, which they had sort of distilled down. And then they did some DPO with, look, QLoRa, our friend, had some data sets, blah, blah, blah. The final version was produced by merging the Evolkit and DPO checkpoints first, which were then merged with the distilled Llama 3.17 dB instruct checkpoint. And then they experimented with some additional stuff, and they were like, nah, actually, let's throw that away. Let's not even do that. I think we did enough. Now you might be wondering, what's Evolkit? You guys already totally understand what this does. It simply takes instruction data, instruction tuning data, and evolves new instruction tuning data from it. This is a synthetic data generation, or SDG process, and one that we talk about in much more depth in the AI engineering bootcamp, because it's even more useful when we get into things like evaluation and stuff where we want to figure out, is our application actually doing the thing we want it to do well? You see, the history here behind merging is people used to literally call these things Franken merges. They were looked down as dirty, cheap, hackers only. No reputable company or person would merge. Of course not. And this was as late as September 2023, people writing this. So MergeKit, fun story. The guy that built MergeKit, we interviewed him on our YouTube channel, and he was like, yeah, I got kind of excited about this problem, and I just threw the GitHub together, and I wanted to see if it worked. And it did work. And then he was eventually merged into the small language model company as a researcher, and he's crushing it now. His name is Charles, and you'll see him out and about. This idea of just kind of getting excited about a problem and building, shipping, and sharing, you'll find it everywhere throughout the community. And it's really not that complicated. And what we heard from Charles when we interviewed him is he's like, I found a few merging algorithms and I'm looking out for more, and I put the ones that I found in there, and that's kind of, what it is. Let's talk about those merging algorithms. The first one is the most simple one. I already alluded to it. It's the linear approach. We're just literally averaging the weights. Now, if you want to be like sophisticated about it, you could call it the model soup approach. Actually, that is what the paper says. And it involves averaging the resultant model weights created by hyperparameter optimization experiments. You can say that. And when we do this, we actually get better accuracy. So, I like the way the paper sort of frames this, where they said, hey, the conventional recipe for maximizing accuracy is to train a bunch of models and then pick one. Model soup says, well, how about that last part? How about that pick one thing? Is that really necessary? The intuition is clear, quite straightforward. There's actually two ways to implement model soup. One is sequentially, you just average, 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 average. And then the next way is a greedy algorithm, where it's a little bit smarter, because instead of just average, 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 we're going to rank the models based on which one performs best on the desired tasks. We're going to merge the best performing model with the second best performing model. Then we're going to evaluate, hey, is it better? And if it's better, we're going to keep going. If it's not better, we're going to be like, yo, that wasn't better, go back. So the greedy one is obviously probably the one you should choose, which is right in line with the way we make decisions about LLMs throughout LLM engineering. The next one is called spherical linear interpolation, which is much less fun than SLRP. So SLRP here is basically all about interpolation on a sphere. This is a weird one. So we kind of have to get geometric for the next two a little bit. It's a more intelligent way to linearly combine parameters, these weights in our model. And what SLRP does is it actually computes the shortest path between 2 points on a curved surface. The paper that introduced this, another OG here, original gangster status, 1985. Ken says, this thing is all about smoothly in-betweening, which is just the best. Real art Ken is producing here, aka interpolating. And the question that he was looking at was how to construct curves on spheres. Now, the classic example, of course, here is as the crow flies, you sort of say, okay, well, what's the quickest way to get from point A to point B on the Earth? And you could basically go straight through the Earth, but obviously you can't go straight through the Earth because that doesn't make any sense. Well, it's kind of the same way with models here for a second. Stick with me. So if we consider that models have weight surfaces, what SLRP is doing is we're able to use this simple idea to compute the smooth path that averages the two models together while sort of maintaining their unique model weight surfaces, okay? Which is a very cool idea. And again, all these things are cool intuitively, but turns out they actually work. And, Ben asks, when you combine models, I'm guessing you take percentages of the two. Well, you can. It depends on the specific algorithm that you're choosing for merging. In the average case, you're literally just taking the average, but you could imagine easily taking some from here, some from there. And as we get into the last one here, there's a really key insight that will be related to this as well in the DARE method. But in order to introduce ties merging, I want to introduce the idea of a task vector or doing task arithmetic, basically doing task math, all right? So if we consider that after we have the final fine-tuned version of a model, we have all the weights, okay? If we took that all the weights model, basically the LoRa adapters, right? And then we subtracted out the entire base model, the one that we froze in the beginning when we were doing LoRa, what we would have left is we would have task vectors. And so, here's a visual representation here. If we got a llama eating sauerkraut, we might take the llama out of it and be left with the sauerkraut, right? I mean, it's a simple intuition here. Let's define task vector more specifically. Let's call it basically this structure that contains the difference, the delta between the base and the fine-tuned weights. This is exactly the idea that we have with LoRa. We're actually putting a structure in that then captures the difference. That's what we're doing. So that, that analogy, Piotr, was spot on. And so when we talk about task arithmetic, we're talking about merging kind of two or more task vectors. And after we merge a task vector, then we can add it into sort of whatever base model, right? So you imagine you have a base model, and then you fine tune one, and then you subtract, and then you have task vector one, and then you fine tune another model, and you subtract, and then you have task vector two. Then you can sort of take these task vectors and you can do things with them. Now, what if you fine tuned though, kind of for similar things? Well, what you can get into is you can get into what you can call smartly task interference, basically an update conflict, where you're trying to sort of say, I want to add this thing that's good at this task over here to this thing that's good at this task over here, but those tasks are kind of the same. So they're really not, adding well. They're really kind of redundant. And when we have this redundancy, that's a big challenge. This is where ties merging comes in, because we can have exactly the same task vectors, or we can also have to deal with different SIGN signs, plus minus. And when we talk about the ties merging method. What it stands for is it stands for trim, elect, sign, disjoint, merge. But basically it says only average the parameters that matter. Only average the parameters that really move the needle on completing that task. Here's a visual representation that we can look at, where we have these sort of task vectors, and we might do some trimming, and then we're going to go ahead and decide, okay, on the SIGN signs, and ultimately we're going to be able to get a merged model that takes the task vectors that we want, that matter the most, that we really care about. And finally, and perhaps the most intriguing insight of all, we can talk about DARE, the drop and rescale. Turns out you can just drop most parameter updates. Most, like almost all of them. You can actually drop, in some cases, up to 99% of parameter updates. So you can basically, you can randomly drop a large number of these updates found in any specific task vector by setting them to 0. And then you can rescale the remaining weights proportional to the ratio of the dropped weights. And it turns out this actually, you know, it's kind of like the classic dropout approach in classic ML. It works super well, and it's crazy. There's also other techniques. So we talked about evol instruct for instruction tuning data. Well, you can evolve, you can imagine sort of evolutionary techniques for merging as well. So I want to go ahead and pause here before we get into fine-tuning and ultimately merging of the next model, because it's about break time. So let's go ahead and take a quick 5-minute, break it out, shake it out. If you guys have questions, you want to stick around, we'll be off the record for the next 5. We can talk about whatever you want. And then again, we'll have more time for Q&A, maybe after the break if you guys would like, or we could do it at the end of class. All right, quick break, everybody. Let's go. Okay, back from the break, we're going to talk about how to merge some models together now, and we're going to merge 2 different fine-tuned models. We're going to create one model where it's really, really good. We're going to call it the Llama 3.1 Riddler. It's really, really good at answering riddles. This is sort of a QA task, but for questions phrased like riddles. Okay. So did you get this one? Are you a Llama 3.1 Riddler? And so basically what we did here is we took the riddle sense data set, did some supervised fine tuning in the exact same way you would expect, quantization, LoRa, etc. And then we've got this model that we can pull off the shelf. Another model that we're going to merge with, again, we want to have the task vector ability here. So we got to make sure we're dealing with fine-tuned models versus base models. This one, imagine you saw some information like this. And it said, by way of example, and not as a limitation, you agree that when using the services and content, you will not defame, abuse, harass, harm, stalk, threaten, or otherwise violate the legal rights, including the rights of privacy and publicity of others. This is the kind of legalese that is very difficult for people that don't enjoy this type of thing, that didn't want to become a lawyer when they were young to understand. And it's actually much easier to say something like, don't mess with us, we'll call the cops on you. And that's what this second data set is able to do. And so we took, again, another model, a Llama 3 model, and we fine-tuned it. So what we're going to do is we're going to basically take this lawyer and we're going to take this Riddler and we're going to merge them and see what happens. Does he get better at both things? Yeah, It does, because MergeKit. Whiz.
Where hopefully you can see my, yes, you can. Okay, perfect. This is how we're going to use MergeKit, because we could use it in our Colab notebook, but it would just be slightly more tedious. So we're going to use the MergeKit GUI. We provide this YAML config. We provide a write token, and we click the merge button, and then the model gets merged. Okay, that's how easy it is. And you might think to yourself, this must be some intensive process. This must be some, GPU, hog. Absolutely 0% chance. Model merging is literally just merge in weights, right? So we're going to look at the notebook now, because we want to have a notebook. And we're going to look at the config. We're going to go through it a little bit more in detail. So we have model, new research, MetaLlama 3, 8B instruct. Okay, cool. We have model, AI Makerspace, legal easy. Okay, I like that one. We have AI Makerspace, Riddlebot V1. You'll notice that we have some parameters for each of these. Now, what this means is that we're going to give, 50% of the weight of our final resultant artifact to each of our models, right? So we have our 50% is going to be legal easy, 50% is going to be Riddlebot. This is what model merging is, by the way. We just say 50%. The technology behind this is entirely, it's like you just wouldn't think that it would work, right? But it does. So what we do is we take the task vector for our legal easy instruct v2. All that is it's this artifact minus this, right? And when I say minus, you might think like, well, what are we minusing? Every weight, right, in our model's network is what we're minusing. So if the weight appears in the model, we're just going to subtract. Easy peasy. Same thing for this, right? We get a task vector for this. And then when we're combining them back together using the ties method, we just make sure that, the density is 50% and the weight is 50% for both of them. That's it, right? So you could see this being extended to even more models. All of this is essentially just an artifact of the fact that most weights in the model do nothing or are not important to our task, right? Which is a tough pill to swallow, considering the amount of billions of dollars that it costs to pre-train these behemoths, 8 billion to 405 billion parameter giants, right? Where most parameters aren't useful. But for us, it's nice. So the one thing that I want to make sure we spend a lot of time talking about in the code is the actual comparison. This is just going to be, pretty straightforward to run. The merging part is so straightforward. It's almost not even worth talking about, right? But the idea is that this works. Astoundingly, this works, right? So the idea basically comes from this, or extends from this fact that most parameters are useless. If most parameters are useless, then it's very likely we're going to be able to find the ones that do matter based on their magnitude, right? So that's what the ties does. When we look through the actual kind of final evaluation here, you're going to see that we use the same old, prompt template for our merged model as we do for our non-merged models. You'll notice, though, that we have our summarized prompt template, which is what was trained for our summary model, and then our riddle prompt template, which is what was trained for our riddle model, right? And when we use the final model, we're going to be able to use their independent prompt templates, and they're going to work the way we expect them to, right? Thanks, merging. Anyway, we go ahead and do this. We create riddle instructions. We create anything else. We load up our base model, which is new researches, MetaLlama 3, 8B instruct. We let this thing rip, right? We ask it to do some stuff. The correct answer is B, candle. It is a decent answer, right? But it's not it's not super duper, right? Like it's kind of a lot of words and everything like that. Okay. So let's see how it does the summary thing. This is the desired summary, right, of the base model. And then this is the summary that it generates. You'll notice that it's longer than the actual, input text, which is most people would agree probably not an effective summary, right? So that's showcasing us the base model is not super good at these tasks out of the box, right? However, with one simple riddle legal easy, right, that we could just pull from the Hugging Face hub, which is actually two models, as you saw here, that are just combined. We can go back to our notebook and we can see, hey, for this response, what's the answer to the riddle? It should be B. The model just outputs B. That's what it's supposed to do, right? None of this fluff, just B. That's the answer. We have this, we have this input text, and then we have the summary. This is a summary, right? But that's pretty good. And the language is a lot more informal, like we wanted it to be, right? And so that's it. That's model merging. I know it's crazy that this works, right? But it does. It's just doing math. The big pieces to keep in mind, right, when we're doing the merging, as you can see here, is that we literally go through every layer of the models. We do some math and we follow some heuristic. So we will spend 1 second thinking about the actual ties reference, which is from this is from our friends at RCAI, right? So ties is the algorithm that's doing this. It's one of many algorithms that you can use for model merging. What I want you guys to keep in mind, right, when you're thinking about this, is that this idea of our task arithmetic or task vectors idea is an extraordinarily powerful and flexible idea, right? If we have if we can take a model and train it and then pull out the thing that was good about it, then we can share that artifact with people to help them get their model up to snuff, right? So when we see things like, in the wild, a model that we're using come out with a better variant on a specific task, right? Instead of like having to recreate it by retraining it, we can just straight up, we can take that task vector and apply it to our current set of information. Someone asked a really good question in the chat earlier, which was, well, what if, is it really good on all of these things? I mean, we see it with this toy example, right? So yes, it's good at the summary. It's good at the multiple choice answer selection. It looks more like what we want. Okay, that's great. But, is it as good at these things? And the answer is because, again, most weights are absolutely not helping us on our task. Yes, right? This is naively applied across the board. And before I let you guys go back to Greg to get us into breakout rooms, I want to mention one more thing about model merging, which is that this is a great way to cannibalize effort, right? So if I'm a business, if I'm an industry, and they're asking you, as say like in an interview style, right? How are we going to get more juice from the squeeze, right? Things like model merging are extraordinarily effective here, thanks to things like model soup, right? Either greedy or more well thought out application where we know that when we're doing experimentation, right? We're trying a lot of different hyperparameters. We're trying a bunch of different strategies to see like which model is finally the best, right? Maybe we're doing something like someone mentioned earlier. We want to train our model to get better at certain tasks, right? Not just toxicity, but toxicity and helpfulness and conciseness, right? And with model merging, what we can do is in all those runs, we can simply merge them all back together to get a model that is likely better at all of these tasks than any individual model, but it is most certainly better at the tasks it wasn't trained on, thanks to that merged information. So model merging seems like a little quaint, fun thing, but it's a massive way to leave less on the cutting room floor, which means that the money you're spending right in your organization for training is being more efficiently spent, which is is not going to hurt your business in most cases. So with that, I'll let you guys get back to Greg, who will take us into our breakout room.
All right. So, was quick question. I just want to expand on this for everybody that maybe hasn't been following as closely as us. Merging really was this kind of out there thing, really not that long ago. And then all of a sudden, like people were like, oh, okay, yeah, it's legit. Really pioneered by RC and MergeKit here, right?
Yes. The thing is when we look at the active, OSS initiatives for model merging, it's basically just RC. So that I think that tells enough of a story by itself, right?
Yeah. There were papers though, right? So it's like
as recent as DeepMind, right? So it's not like small shops are worried about merging, right? Google DeepMind with Warp Fusion very recently. At NeurIPS just 2 days ago or whatever, we're seeing people apply really naive model merging strategies to things like RLHF and DPO, right? To get better at that alignment process by kind of expanding our search, right? And one of the most beautiful things about model merging through something called SLRP, which is just one of the many methods we can use, is that we've been talking about like, well, we want to make sure we don't drift too far from the reference, right? Our policies shouldn't get too far away from our reference. Well, with something like SLRP, we can literally slurp it back to the reference, right? We can merge the final artifact back towards our reference model in order to just mathematically verify that we haven't drifted that far. So this technique is extremely flexible. There's a ton of awesome research constantly ongoing. For us, people who are going to build with these things, the only company is RC that's actually letting us do it today. Open source way.
But as enterprises have many hundreds or thousands of models, then I mean, literally, they will become experts within each organization that will have all the models in their head and think about potentially merging them later, right? And if you can get away with one model that's the same size or even smaller than other models, then maybe you can save money, And so like there's a lot of potential. Okay, there's a question in the chat that I just want to address just because we have a little bit of extra time here. So there seems to be some misunderstanding about base model versus fine-tuned model. I wonder, could you pull up a base model and show us an example output real quick while you tell us about the difference? So my understanding, and this is really clear when you start using these base models, and it goes right with the language, okay? It's not instruction tuned. Instruction tuning means you're generally getting better at following instructions. And when you do a specific task, you instruct to do that specific task. But the problem is that's just for one specific task. So if you have many different types of instructions, you're sort of generally getting better at listening to humans and following their instructions to accomplish specific tasks. And so as we saw in the InstructGPT paper, the base models are really bad sometimes at following instructions, which is still true today. And this is why it is an absolute best practice standard to not use the base model. Literally, don't pull it off the shelf. Don't use it. I've never heard of a use case where people should use the base model instead of the instruct-tuned model. So can you show us like a fun example real quick, Wiz? Of like a terrible base model output just for fun here?
Yes. Let me make sure that I can get one. I'm just grabbing one.
Extra terrible. Yeah.
Extra terrible.
I'm making him do it on the fly, guys. This is just for you guys because you're asking for it. You guys that are still here with us, you guys rock. So, and then we'll go into breakout rooms.
Yeah. So basically, when we're talking about base models, we are looking at, and boy howdy, is it turning out to be hard to find just a base model that's
I mean, this is what we did during pre-training, right? We're just pre-training. That's the base model.
The idea is, I will continue to try to find an example of it happening live. But the idea is that a base model you can think of as purely a completion model. So the idea of a base model is that we have no idea of instruction following. We have no idea of here we go. We got 1B.
These are different objectives. That's what you're saying. Yes.
Yes. Okay. So we have once upon a time, there was a man who was very rich. He had a lot of money. He was very, whatever it's going to say. But if I ask it, count how many are in the word strawberry, right?
Oh, yeah.
And I hit compute, it's not gonna look at that, and say, oh, this is a task that I should do, right? This is a thing that I should be there is no concept of an instruction to this model. It's just really good at choosing which token is probably going to come next based on our thing. So if I say, the weather in San Francisco is right, and I compute. Imagine I spell San Francisco right. A bit of a mixed bag. It'd be sunny warm one day and then rain cool. That's what it's good at, right? It's good at finishing sentences, at predicting the next token. It's terrible at every other objective. And that's why instruction tuning is such a big deal. Now, to be very clear, base model in the context of model merging just means the model that you started with. So very oftentimes, that's actually going to be an instruction tuned model that's already okay at a bunch of tasks. As we see in the notebook, right? We're starting with model that is good at following instructions, 8B instruct. We're not going to start with the base model because the base model is so terrible. But this all does apply to that as well. So when we say base model in context of model merging, we mean the weights that we start with. Because remember, through LoRa, right? LoRa lets us train those too many adapters that too many matrices that we can kind of glue back together, and then we can plug that into our original model, and then it's going to represent some delta weight, right? So the idea with the base model versus the task vector in terms of model merging is exactly the same thing. We just look at delta weight as opposed to thinking about our weights as this one immutable object, and that's extremely powerful. This pattern, in fact, again, just to shout out some recent work, right? Things like that actual weight update for your fine tuning, you can quantize in 1 bit. With 1 bit representation, you can quantize that. That's the idea of this delta weight. It's the changes we've made as we've fine-tuned, customized, aligned, whatever we're gonna call it. Yeah.
That's right. That's right. So then the predicting of the next token that we learned to do during pre-training is different, as we've seen through Instruct GPT, through instruction tuning, through alignment, following instructions helpfully and safely. And so we've got a couple more questions in the chat. I mean, I'm going to keep it rolling here. Base model means different things depending on the context. It certainly can, as we just talked about. And again, guys, what we want to do is we want to focus in on the fact that people are using these words because they think they're descriptive. And out at the LLM edge, we're always disambiguating language, whether it's base model versus reference model versus fine-tuned model. That's going to be your job to figure that out as you guys are out there leading from the front. Okay, back from the breakouts. I want to just throw a quick shout out to anybody that might have an interview coming up. What you might hear on this kind of front is how can we get more out of our fine-tuning process? Is fine-tuning useful? And one of the answers that I would suggest is kind of what we talked about earlier. You can imagine a future where many companies have many tens or hundreds or even thousands of models. The AI engineering team is going to be at the center of that, looking across models, how these could be merged, how these could be supporting inference for different types of tasks in a more cost-effective way. This is going to be incredibly useful in the future of enterprise. Stay tuned. And, that's how you should answer it. And they'll be like, wow. Today, we talked about DPO. We talked about merging. We talked about the different algorithms. And before we take feedback today, we'd like to answer any questions you guys have for the next few minutes. So best practices for alignment, Wiz. Do alignment.
Was it best practice alignment, or what did it say? Best practice optimization or something?
Yeah, it's sort of a best practice alignment technique.
Okay.
So, I think if you're going to go ahead and pick a technique off the shelf, I would pick DPO first, and that would sort of show whoever you're working with. Nalay is legit.
So
Yeah.
DPO would take precedence over fine tuning.
Over RLHF.
Okay, over RLHF.
Yeah, yeah.
RLHF will take precedence over fine tuning. Or
Remember, RLHF is like a super fine tuning. So you want to do like the meaty cut fine tuning regular SFT. And then if you want to further dial in and optimize and further refine and go in and very finely tune, that's where you use an RLHF or DPO.
got it.
We can think of them as a flow chart, right? Like, so SFT, so full fine tuning, we're going to do that first, and then we are going to do an alignment strategy, RLHF or DPO. We would recommend DPO.
Just to confirm from Martin Alexander, standard merging, you do two fine-tuned models that have the same reference model, does not require a GPU.
Correct. Correct. We don't need it. It's so simple. We can let the CPU do it. Amazing.
Well, you're just adding numbers, right? Like but won't you need a GPU to actually validate that, to test it against the training set or validation set, to see if what you're getting is what you want, or if you actually went backwards?
Absolutely true.
That's
Yes.
true. Yes.
So I just remember one of the missed question in the interview. They asked, what are the methods for optimization of some methods for optimization of language models? Did they mean the quantization or DPO or?
Quantization can be an answer to that
Well,
question.
yeah, I mean, the follow-up question is like, do you mean optimization for inference or optimization for training and alignment? That would be the follow-up question, right?
How about the inference, if this is the follow-up question?
Well, you could talk about quantization, standard quantization, or like we've covered AWQ, activation aware, weight quantization. I believe you've made a post about that, if I'm not wrong, Sahar.
Yes,
I would bring that one up as a best practice. And then if you want to be really out there, maybe talk about vector pre-trained or vector quantization. I think it's
VPTQ.
I forget what the P is. It's VPTQ from Microsoft. Yeah.
Thank you.
A classic.
Yeah. Ashwin, I think when we're saying, in a sense, I see what you mean, but I think when we talk about sort of training versus inference, we're talking about sort of getting the model and changing the model weights versus just freezing the model weights, never changing them again, and just doing inference. So when we talk about merging, since we're actively changing the model weights, I would put that in the training category instead of the inference category.
It's also not an optimization, unfortunately. So your weights are in whatever precision they're already in, and then there is no merging strategy that is inherently tied to a inference performance benefit. So that's another sticky kinds of wording here exists around words like performance, right? Because performance is a big word. But what we mean by like inference optimization is we're talking about performance as in how many tokens you can spit out, not as in how many, how good are you at this task, and in terms of like a metric like accuracy or something. And the question from Nitin, MergeKit evolve is just MergeKit with that evolution algorithm tied into it.
Yeah, maybe one more question if anybody has one.
Any large elements of LLM engineering that you didn't get to cover that we wish we had time to cover is a tough one. For me, I'm going to say no.
I mean, no, fundamentally. And if there are, we're going to squeeze them in next time. So like So like even today, I saw, it was like Andrew Ng was talking about mixture of experts or something. It's like there's always something next. And I think, you could get into non-transformer architectures and stuff, and we've thought about that, but I think ideally personally I'd like to do again more justice to some of the depth of some of the math, I think, in the future coming out of this, rather than do more hypey stuff, do the stuff that I know isn't going anywhere.